Good morning and welcome to Affiliate Network Consult. Our topic for today is IPv6. Today we are going to treat how to convert binary numerals to hexadecimal and vice versa. After that, we also introduce ourselves to IPv6 addresses. Then we come to the IPv6 address format. After that, we'll finish up with how to subnet IPv6 addresses. So let's start with conversion. We are going to use this table, what we used in IPv4. 16, 8, 4, 2, and 1. Then also we are going to add the hexadecimal reference table, which is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Then we have A, B, C, D, E, and F. A represents 10, C 12, 13, 14, and 15. This is the hexadecimal table. As we all know, the hexadecimal numeral shouldn't be more than 15. It's a number to the base 16, so all the numbers are below 16. Okay. So let's start off by converting this binary to hexadecimal. Since hexadecimal is a number to the base 16, this chart over here, we are not going to use this part of the chart since every number there is more than 16. So we are only going to use this part of the chart, meaning from 8 to 1. That is what we are going to use, 4 digits in all. If that is the case, then the 8 digits that we have here, we are going to separate them into 2 so that we can have our 4 digit here and 4 digit here. Bringing down this table, you put your 8, 4, 2, and 1 here. You do the same to this part. 4, 8, 4, 2, and 1. 8 has 0 under it, so 8 is off. 4 has 1, so we are going to add 4. 2 has 1, plus 2, and 1 is on, plus 1. We have a total of 7. 7 from the reference table is the same, nothing changes. So we leave it as it is. Coming to this side, 8 has 1 under it, so 8 is on. Then we add 4. 2 is off because there is 0 under 2 and 1 is on. So we have a total of 13. 13 on the reference table here represents D. So 13 is equal to D. So the conversion from this binary numeral is D7. This is the hexadecimal equivalent of this binary numeral. So what points again are we learning here? We have learned that a digit in the hexadecimal represents 4 digits in the binary. It's a very important point that we have to take note of. Just one hexadecimal digit, as we are seeing here, 7, represents 4 binary numerals. So how many binary numerals will be D7. How many bits? 8. We know a bit is either a 0 or 1. So D here represents 4 bits, 1, 2, 3, and 4. D7 is 8 bits long. Let's take another example. Convert 11111101 to hexadecimal. Same procedure, so we separate this 8 digits into 2, 4 here and 4 here. Bringing down this part of the chart, we have 8, 4, 2, and 1. Same here, 8, 4, 2, and 1. 8 has 1 under it, so we turn it on, plus 4 has 1, plus 2, and plus 1. We are adding everything here. Totaling 15. 15 from our hexa table is F. So 15 is the same as F. Here we have 8 is on, 4 is on, 2 is off. So we add just 1. That will give us 13. 13 from the reference table is D. So we have FD. FD. 1, 2, 3, 4. 1, 2, 0, 1 is equal to FD in hexadecimal. So you see 8 bits here is represented by these 2 characters in hexadecimal, meaning F alone is 1111 and D is 1101. 1 digit in hexadecimal represents 4 bits. Okay, so now let's treat how we can convert from hexadecimal to binary. Same principle. So as an example, we are going to convert 3D into binary. 3D. So we are going to separate 3D into 2, 3, breaking 3 down using this chart. Is part of the chart. Here, 8, 4, 2, and 1. We want to break 3 down using this part of the chart. 3 is 2 plus 1. So 4 is off, 8 is off. So now the 3 we have 0, 0, 1, 1. How about D? D from our chart is 13. Breaking 13 down using this part of the chart is 8 plus 4, giving us 12, plus 1, 13. So 2 will go off. So now D is 1, 1, 0, and 1. Combining these 2 together, 3D becomes 0, 0, 1, 1, 1, 1, 0, 1 in binary. Let's take another example. So F5. Convert F5 into binary. Separate them into 2. F from our hexa reference table is 15. Breaking 15 down using this part of the chart will give you 8 plus 4, which is 12, plus 2, 14, and plus 1, 15. So every single bit is turned on. F has been represented by 4 bits. That's all ones. How about the 5? 5 from the hexa reference table stays the same. It doesn't change. So breaking 5 down here, we have 4 plus 1. 2 will be off, 8 will be off. So 5 is 0, 1, 0, and 1. Combining all of them together, F5 will give us 1, 1, 1, 1, 0, 1, 0, 1 in binary. So now we are done with conversion. Let's introduce ourselves to IPv6 addresses. So IPv6, what is an IPv6 address? An IPv6 address is a 128-bit address system, as opposed to IPv4, which is just 32 bits long. Remember, a bit is either a 0 or 1. So if you write 0, 1, 0, 1, 1, how many bits do we have here? 5 bits. IPv6 is 128 bits long. And it's written in hexadecimal format. It's also separated by colons. So let's take a typical example of an IPv6 address. We have 2001 colon 0D B8 colon 0000 colon 130F colon 0000 colon 0000 087C colon 1408 1, 2, 3, 4, 5, 6, 7, 8. This is a typical example of an IPv6 address. Each digit here is a hexadecimal. So the 2 here is hexadecimal. And what is the 2 in the binary format? It's 0010. What about 0? 0000. And this 0 is also 4 zeros. And the 1 is 0001. So how many bits do we have in all? 4 bits plus 4 bits plus 4 plus another 4 is 16. So each hextet, what we are seeing here, you can call it hextet or quartet. In some books, you see hextet, in others, you see quartet. The number which is separated by a colon is 16 bits long. So we have 16 bits here, 16. Each quartet or each hextet is 16 bits. And we have 8 of them. So the first quartet, second quartet, third, fourth, fifth, sixth, seventh, and 8. Each one is 16 bits. So 16 by 8 will give us 128 bits. So that makes IPv6 addresses 128 bits long. Now this address that you are seeing has parts in it just like IPv4. So from this part to this part, the first 48 bits is called the provider and it's 48 bits. This 16-bit here is also called site. You can also call it subnet. Then the last 64 bits is what we use for host addresses. You can also call it interface ID or just host. So suppose you want to assign IPv6 addresses, you are going to use this part, the 64 bits, to assign addresses to devices. So still introducing IPv6 addresses. IPv6 addresses offer numerous address space. Let's refer to a document here. Yeah. So we have 32 bits for the IPv4, which is 4 billion addresses. IPv4 can offer 4 billion addresses. Initially, it was thought that IPv4 addresses would never go off, but that was wrong. Now it's gradually being replaced by IPv6, which is 128 bits long. And there's the address space that they can offer. Very difficult to mention. So comparing IPv6 to IPv4, we have the entire IPv6 address to be the entire IPv4 address space. That is 2 raised to the power 32 multiplied by 2 raised to the power 96, which is a lot of addresses. Let's try to relate how the address looks like. So supposing we are coming to share the entire IPv6 addresses to the population of the world. As at the time this document was being written, there were 6.5 billion people on Earth. So each one is going to receive an IP address, IPv6 address. If we share, each single individual is going to have 52 trillion IPv6 addresses, which is a lot. So what are you going to do with these addresses? Let's assume each individual wants to share the allocated IPv6 addresses to their brain cell. So the average brain cell of every human is 100 billion. So you are going to share your 52 trillion addresses to each brain cell. So how many addresses will each brain cell have? 523 quadrillion addresses. So now we can relate how numerous IPv6 addresses look like. A lot of addresses. Still on the address format. So now we see a typical IPv6 address, how it looks like. Very cumbersome to write. Very cumbersome to write. But we still have to get used to it. Because at the time we are living in, and IPv6 is so inevitable. We need it especially as we are moving to Internet of Things. IP version 4 cannot solve that solution for us. So we have no choice than to learn it. Let's look at another example of IPv6 address. So 2001:0F 2C colon 0000. Do we have our 8 quartets? Let's count. 1, 2, 3, 4, 5, 6, 7, 8. Yes. So we have a typical IPv6 address. As said earlier on, the first 48 bits is for the provider of the address. So 48 bits belongs to the provider ID. Then we use this 16 bit here for our subnet. You can also call it site. Subnet or site. Then our last 64 bit is the interface ID. Or host. So to write this IP address, for it to be meaningful, just bring a /64. What they are trying to say is the first 64 bits belongs to the network. That is from here. Let me use a blue pen. From this part all the way to this part here belongs to the network. First 64 bits. So if you are asked to write the network ID for this IP, this is a host address. It actually belongs to a host within a network. So you've been asked to write this address as a network ID. It's going to be 001 colon 0F26 colon 0000 0000. Then all the host bits will be turned to 0. This represents the network identifier, network ID. Remember, the network ID, every bit in the host portion is 0. So from here you can start assigning your IP address 0001, 0002, 003, keep on adding 000A, 000B, and so on and so forth. Because of the cumbersome nature of IPv6 addresses, attempts have been made to shrink the address. It's not comfortable writing this whole lot of addresses. So we are coming to learn how we can shrink an IPv6 address. There are rules for it. Now the first rule says, rule number 1, omit leading zeros. So every leading 0 here is going to be omitted. This is a leading 0. This is also a leading 0, not trailing zeros. Trailing zeros are not part. So we're going to omit the leading zeros. So let's do it. 2001 colon F26 colon 1234 1234 EDC 1234 1234 and 1234/64. Rule number 2. If you have all zeros in a quartet or a hextet, you can just reduce it to 1 0. So if every digit in a quartet is 0, just reduce it to 1 0. So let's do it. 2001 colon F26 colon 0 colon 0 colon EDC colon 0 0 and 0 slash 64. So you see we've shrunk the address. We can still go further. Rule number 3 says if there is a consecutive 0, just represent it by double colon. So if you have consecutive zeros, continuous zeros, you are going to represent them with just double colon. And this double colon does not repeat itself in an address. You can repeat double colon in a single address. So over here, you can tell that we have one set of consecutive zeros and another set of consecutive zeros. So you have to decide where to place it. You can choose to write it this way: 2001 colon F26. Then this set of consecutive zeros will be double colon. Then you continue with EDC. Then you have your 0, 0, and 0. This is correct. You can also choose to bring your consecutive 0, your double colon here. This part of consecutive zeros is also correct. So either this or 2001 colon F26. Then you are going to repeat this in that case: 0 colon 0 colon EDC. Then this set of consecutive 0 becomes colon colon slash 64. This is also correct. Remember, you cannot repeat the double colon twice in an address. So if you choose to write the address this way, 2001 colon F26, then you decide to bring a double colon here and continue with EDC. And when you come here, you bring another double colon. It is wrong. It is not accepted. We don't accept this. So this is how you can shrink an IPv6 address. I think shrinking an address makes the address look better. So whilst you're able to shrink an address, you should be able to expand an address if you are given. So let's try the reverse trick on expanding an address. Let's see if we can expand the following address. So supposing you have FCDE colon 3A colon A4 slash 64. If you are asked to expand this IPv6 address, how is it going to look like? First, note that leading zeros are omitted. And also we have 4 digits or 16 bits in each quartet. So over here, the 3A is missing 2 leading zeros. You put it there. Let's bring our double colon here. Then this A4 is also missing 2 leading zeros. So A4. Knowing that every single IPv6 address should be 8 quartets. But what do we have here? We have just 1, 2, and 3 quartets. So how many quartets are missing? 5. But what do you see here? Double colon. Double colon represents continuous zeros or consecutive zeros. So how many consecutive zeros do you think we have to add up to these 3 quartets for it to be 8 quartets? 5. 5 continuous zeros. So expanding the address, we're going to have F, C, D, E, colon 003A. Now 5 consecutive zeros. So 3, 4. The last one, then we have our 00A4. This is our expanded IPv6 address. So each time we are given an address, we should be comfortable to either shrink it or expand it. We have to be very skillful in this area because it helps a lot. Let's move to the next item. We are going to see how we can subnet IPv6 addresses. Of course, IPv6 addresses, we don't do bit borrowing, but we still subnet. Let's throw back to the IP version 4 days. So we need a previous knowledge here. Subnetting IPv6 addresses. So throwing back in the IPv4 days, supposing we have this class B, 172.16.0.0/16, and we are to submit. We have this network. We have a router here, another router here, a router here. We have our network here, another network here, another network here. And we want network IDs for network A, network B, network C, D, and E. Even though network B and D are point-to-point network, but don't worry, we are going to use equal length subnet mask. So, using this octet, that's the first 8-bit here, for our subnets, we are going to borrow 8 bits, correct? So our first subnet, since the block size of 8 bits is 1, our first subnet is going to be 172.16.1.0/24. Subnet 1. 2 will be 172.16.2.0/24. Subnet 3 will be 172.16.3.0/24. Then on and on we go. 172.16.4.0/24. You see, we are using the third octet. Okay, we are playing with the third octet. So we can decide to give subnet 1 to network A. So this network A will have a subnet of 172.16.1.0/24. So supposing you have computers or devices in this network and you want to assign IP addresses to them, this is a network ID. It cannot be assigned 172.16.1.0, but the usable IP addresses will start from 1.1, 1.2, 1.3, 1.4, and so on till you get to 1.254. These are the valid IP addresses. So now, as a refresher, we know the difference between network IDs which cannot be assigned and valid IP addresses which can be assigned. Network B can also have the second subnet, 172.16.2.0/24. 2.0 cannot be assigned. The valid IP addresses within the range are 2.1, 2.2, and so on till you get to 2.254. As I said earlier on, fine, this network is point to point, but that's not the point we want to make here. We just want to establish the fact that a /16 can be assigned using a /16 can be subnetted using the third octet. Okay, so network C can also have 172.16.3.0/24. Valid IP addresses within this range will be 3.1, 3.2, 3.3, and so on. Then network D can be given this. It moves on like that. So with this in mind, let's see how the IPv6 world will look like. The IPv6 subnetting is so simple because we don't do bit borrowing. It doesn't exist in this world. So posting, we have this address FC:02F_D:/ABCD:0000. One, two, three, four, five, six, seven, and the last quartet like this /64. Remember, if you are to shrink this address, it will be the same as FC:00 2FD ABCD and double column /64. This is the same as the address above. If you are asked to subnet this address, what are you going to do? Just like the IPv4 address we saw earlier on, this part is for the interface ID, or where we use to assign IP addresses to host, and it's 64 bits. We use this portion, this 16 bit here, to subnet. And this is the actual network bit. So, using the 16 bits here for our subnet, the first subnet will be FC:00 02FD ABCD. Then our subnet portion, our first subnet can be 0, 0, 0, and 1. Continued by 4 consecutive zeros. So double colon /64. This is our first subnet. So assigning addresses to our, let me just expand our first subnet for us to have a clear picture of it. So let me continue with the 4 consecutive zeros. One, two, three, 4 /64. So that is the network identifier. If you want to assign an IP address from this network ID, remember this network ID cannot be assigned to any device since it has all the host bits to be 0. So our first usable IP address will be 2FD, A, B, C, D. Then you bring your subnet ID. Then all zeros and 0001. That's the first usable IP address. Then it will continue like that. The next one will be 0002, colon 0003, 4, 5, 6, 7, 8, 9, 00A. We don't have 10. So you have A, B, C. Continue. You have a lot of IP addresses to offer within this range. So this will be the usable IP addresses, and this is our network ID. The second subnet, subnet number 2, because of space, I'm going to take advantage of this very address space. Subnet number 2, what will change is just this portion. 0002. Then the rest will come. So in assigning IP address to the second subnet, we have FC00, then this will follow, this will follow. Then after that, what will change is the network portion. So we have 2 here, and the first IP address will come. You can decide to write the first IP address as FC002FD. That's if you want to shrink. A, B, C, D, then 2, just 2, because these are leading zeros. Because we have 3 consecutive zeros here, you bring your double column. Yeah, just repeating this IP address. You want to shrink it. 3 consecutive zeros, double column, then 001 will be just 1/64. That is the first usable IP address. Within this subnet, the point we want to make is we use the 16 bit here to subnet. So supposing you want to design an IPv6 network, just as we did for the version 4, let's see how we can do that. Let's design a network topology with just 3 routers. Okay, so we have this network. This is our first router. Our second router, you connect it to another router, then you have your networks here. So this is an IPv6 network that we want to design. Network A, network B, network C, network D, and network F. We want subnet IDs for them, or network IDs, before we can derive usable IP addresses using this main address. Having in mind that we can only use this part here to subnet. Straight away, we don't have to stress ourselves. So our first subnet, subnet number 1, will be FC00. Writing down this, I have 2FD colon, this will come, A, B, C, D. Then the subnet portion, my first subnet, will be 0001. That is my first subnet. After that, I have 4 consecutive zeros. So without worrying myself, I bring my double column and a /64. This is my first subnet. My second subnet, from this first subnet, I can derive several IP addresses. I can derive several IP addresses. Let's have a picture before we move on. So my first IP address from this subnet will be the whole of this here, then colon 1. It's a usable IP address. Colon 2, having in mind that this colon represents the continuous zeros you are seeing here. Another address, colon A, it can be colon EF, and so on. All these are going to be valid IP addresses that you can use within this subnet. So our second subnet will be FC00 colon 2FD colon ABCD. You repeat everything in the provider end. And when it gets to the subnet end, it will change 0002 for the second subnet. And since we have consecutive zeros, you represent it by double colon. Our third subnet, FC00 2FD ABCD. Then the changes will happen here. 0003. It can even be A. Anything. Or C. Double colon 64. Fourth subnet, FC00 2FD ABCD 00EF. I just want to add change it to any figure here to stress on the point that this subnet portion is where the changes will happen. Then you bring your double colon 64. So you can decide to give this subnet number 1 to network A. So this network A will have a subnet ID of this. Just as we did for the IP version 4, the subnet ID will be FC00 colon 2FD colon ABCD, then colon 1, because we have 2 consecutive zeros here. So I'm omitting the first 3, the leading zeros here. Then I bring my double colon /64 just for this subnet. You see how long the address is. So if I have devices within this subnet and I want to choose, remember you cannot assign this IP address to any device. If I want to choose IP addresses for devices within that network, then it will start from FC00 colon 2FD colon ABCD colon 1 colon 1 colon 2 double colon 3 double colon 4, and it goes on. All these are valid IP addresses that you can assign to devices within that network. Come to network C and you want a subnet ID for it. You choose this one, the second subnet here. For network C. So valid IP addresses for network C will also be FC00 2FD. Let me make use of space. FC00 2FD colon ABCD, and the subnet is 2 here. I'm omitting the leading zeros, so just bring your 2, then colon double colon 1. That will be the first usable IP address. 2 double colon 2 double colon 3 double colon A double colon B C D, and so on. The identifier or the distinguisher is what we are seeing here. Okay, these are the distinguishers. This one will create the subnet identifier. So it's simple. That is how IPv6 addresses are subnetted. This brings us to the end of our lesson. I hope you enjoyed it. Please look forward to our next video where we are going to discuss how to assign IPv6 addresses. In it, we'll see the manual IP address assignation, the automatic using the EUI 64 bits, and also the DHCP. Thank you for joining us.